Ready? All right, hi everyone. Welcome to our physics permanent colloquium. I'd like to introduce to you all Dawn Williams. Dawn is a professor at the University of Alabama, and she's a member of the IceCube collaboration, and she's currently the analysis coordinator, so that's in charge of all the analyses that come out of the experiment. She is an astronomer by training, so did her PhD in astronomy at UCLA, but found herself on the interface between astronomy and particle physics, and has, I guess, moved kind of in that direction towards leading neutrino astrophysics. So, without anything else, I'd like to introduce them.
Yep. Thank you, Lauren. Thank you all for having me here today. It's a pleasure to be at Stanford. I actually did my master's research at SLAC on the Ascarian effect, so it's been a while. So I'm here to talk about IceCube and neutrino astronomy. IceCube does a lot of physics and astronomy, but it's this particular area of multi-messenger astronomy and neutrino astronomy that I want to focus on today. So I'd just like to acknowledge the IceCube collaboration. This is our current collaboration map. The US, Canada, several countries in Europe, especially Germany, Belgium and Sweden, Australia, Japan, South Korea, and New Zealand. And it's about 300 people at over 40 institutions. It takes a lot of people to make this collaboration run. Okay. So multi-messenger astronomy is the theme of today's talk, especially neutrinos. And when we talk about multi-messenger, we talk about the different types of particles or waves that we're detecting from astronomical objects and how they're all connected together. So the four messengers, gamma rays is what's represented here, but that is the highest energy end of the electromagnetic spectrum, and obviously astronomy is done in all areas of the electromagnetic spectrum. Cosmic rays have been around for quite a while. These are charged particles, and because they're charged, they get bent in magnetic fields. That's what this is. That makes it challenging to point them back to their sources, but they are a very valuable source of information about processes going on in astrophysical objects. Neutrinos is what I will focus on. These are neutral particles, very difficult to detect, and they're very interesting because they can come from deep inside of objects, which might be otherwise opaque. And of course, the new kid on the block is gravitational waves. With the detections by LIGO, this is a very exciting era because sources of gravitational waves have also very recently been discovered to be sources of electromagnetic waves as well, with the detection of a neutron-star merger. There was also a gamma ray burst, and this is a very exciting time to see all these things working together. And dark matter is still out there, but that is definitely going to be part of this picture going forward. Sorry, let me switch out my dongle. The presenter doesn't seem to be. Okay, so neutrinos are standard model particles right here in the standard model version of the periodic table, and they come in three flavors: electron, muon, and tau. They're the lightest particles that are known. They do have mass, but it is very, very small. And of course, it is known that these can change between flavors in transit because the flavor eigenstates are not the same as the mass eigenstates. And there are many, many sources of neutrinos, both at home and in the cosmos, going from the cosmological neutrinos at the very low energies that are relics of the Big Bang, the neutrino equivalent of the cosmic microwave background, all the way up to cosmogenic neutrinos, which are neutrinos that would be produced by cosmic rays interacting with the cosmic microwave background. And most of these have, in fact, been observed. Of course, in between, we've got solar neutrinos, supernova neutrinos from 1987A, and then reactor antineutrinos, terrestrial antineutrinos, and background from old supernovae, which we expect to be in part of the general flux. Atmospheric neutrinos, these are produced by cosmic rays interacting with our atmosphere. And then neutrinos from AGN is what it's labeled here. More generally speaking, neutrinos from cosmic ray accelerators. Neutrinos from the sources of the highest energy cosmic rays are what I will focus on here today. And most of these have been discovered, but as cosmological neutrinos, still as yet undiscovered, high flux, but very low energy, very challenging. A background from old supernovae, that's what Super K is going after with the gadolinium update, and cosmogenic neutrinos. There are many experiments in progress trying to find these, many of them based in the radio, but the rest of these have been observed. So neutrinos from cosmic accelerators. So what is prompting this idea that, what caused us to build this detector that I will describe is the fact cosmic rays have been observed all the way up to energies of about 10 to the 20 eV, one a little bit higher than that. And this spectrum, these energies are much higher than what we can achieve on Earth in accelerators. So the question is, what is accelerating these particles? And it is believed that they're accelerated in astronomical objects, objects which have very strong magnetic fields, objects which have strong shock waves, things like active galactic nuclei, the jets of active galactic nuclei, gamma ray bursts, supernova remnants, objects like that. And where these cosmic rays fit into the picture with the other messengers, particularly gamma rays and neutrinos, is that where these protons are being accelerated, they should also be interacting with their environments. If they interact with gamma rays in their environments, then you can get either protons and neutral pions or neutrons and positively charged pions. And if you get the protons and then the neutrons, which then eventually decay into protons, these can form part of the cosmic ray flux, as well as particles which didn't interact. And then from the neutral pions, they always decay to gamma rays, so that could form part of the gamma ray flux. Of course, there are other ways of getting high energy gamma rays, such as inverse Compton, but this is how the gamma rays would fit into the picture with cosmic ray acceleration. And then if you get charged pions, then they will decay to muons, the muons will decay to electrons, and along the way you get the associated neutrinos and antineutrinos. And if you have protons interacting with protons, then you can get both positive and negative pions as well as neutral pions. So all of these things are connected together in this fairly simple picture of cosmic ray acceleration and cosmic ray interaction with their environments, whether it's gamma rays or protons. And therefore, it is interesting to look for neutrinos from these sources. Now, if you look at the flux of cosmic rays and make a calculation as to how many neutrinos you would expect, or can at least place an upper bound on that, it was known for a while that in order to detect the type of fluxes we expect from cosmic ray sources, we would need a very large detector. And in fact, a cubic kilometer detector, you would see about 10 of these neutrinos above the atmospheric background per year. So you have to go to very high energies in order to get away from the atmospheric neutrino background, which is tremendously high. So this brings us to IceCube. This was designed specifically to detect neutrinos from cosmic ray accelerators, a neutrino flux that was motivated by the flux of observed cosmic rays. And so IceCube was built in ice at the Amundsen-Scott South Pole Station, that is right near the geographic South Pole. And cube is for cubic kilometer, that is the instrumented volume of the detector. So this is what it looks like, a cutaway from the ice. On the surface, we have our ice top array, which is a cosmic ray air shower detector and also a partial veto for the deep in ice part of the detector. The modules are deployed on cables in holes that were drilled into the ice with a hot water drill, and the sensors start at 1450 meters deep and go down to 2550 meters deep, and then there's some ice below us and then the bedrock. And in the center of the detector, we have a more densely instrumented array called deep core. I won't be talking much about that today, but that is aimed at more low energy physics, neutrinos in the tens of GeV, which is low energy for us. And that goes for neutrino oscillation and attempts to indirectly detect dark matter. There are 86 of these strings, and each of them has 60 sensors, which are called digital optical modules, or DOMs for short. And the detector was completed in 2010, commissioned in spring of 2011, and it has been running continuously since then. We have over 99% uptime. We run 24 hours a day, 7 days a week, 365 days a year. So we cover a very broad range of physics in IceCube. I'm just going to be talking about the neutrino astronomy and multi-messenger astrophysics, but we also do cosmic ray physics with IceTop, and we do neutrino physics, as I mentioned, with deep core oscillation physics, muon neutrino disappearance and tau neutrino appearance. We search for dark matter indirectly, not directly, but indirectly, looking for signatures of dark matter in neutrinos. We also search for other exotic particles, such as monopoles, and we do glaciology because we have the most detailed information available on the ice at the South Pole at these depths, much more detailed than what's available from ice cores, and so we've published papers in glaciology journals and talked to glaciologists as well. So this is the IceCube sensor, the Dom. It's a fairly simple sensor. It's a pressure vessel which contains a single photomultiplier tube, a 10-inch photomultiplier tube, which faces downward. It's potted in some gel that makes optical contact with the glass. And then what makes it digital is the main board. So this contains digitizing electronics, so that we can digitize the signal in ice and send it up over the cable rather than sending an analog signal, which will get distorted. And this enables us to get the complete waveform information from the voltage signal recorded by the PMT, which enables us to do very detailed reconstruction rather than doing something simpler like a time over threshold approach. There's also LEDs for calibration. There's 12 of them on each module, so there's over 5,000 of these in the ice. Each of them has 12 LEDs, so every DOM can act as a calibration source as well as a receiver. So the ice, that is an important part of our detector, even more important in some ways than the sensor itself. It is our support structure, it is our calorimeter. We didn't design it, right? We didn't have to pay for it, it was free, but that means we have to take it as it comes. It is a naturally occurring volume of ice, and it is quite complicated. So in undisturbed ice, at these depths, there's no bubbles. So we're deep enough that bubbles are incorporated into the crystal structure as clathrates. So, but note the word undisturbed, that's very important. We do have layers of dust, volcanic dust, and also dust just from glacial events. That's actually most of it. This causes depth-dependent scattering and absorption. So this is what our scattering looks like as a function of depth. This is as a function of wavelength here. That's fairly flat on this scale. And then the absorption as a function of depth. And where these things are high on the absorption and scattering scales, that means that light does not travel as far undisturbed. So this right here at about 2,000 meters depth, that is right in the middle of the detector depth-wise. So we call it the dust layer, and then we've got smaller dust layers as well. The dust layers are not horizontal. The glacier has been, traveling. It travels at 10 meters a year, and so these layers actually get bent. And so this is just a relief map showing the tilt, the gradient tilt of our dust layers as a function of depth. So the tilt is stronger at larger depths. We found out the scattering was anisotropic. We did not expect that at all. But this is a plot showing both simulated and real muons, and if we divide them, whether simulation assumes no anisotropy, we get this pattern here, okay, and that basically aligns with the flow of the glacier. Whatever the scattering are, the dust grains, they seem to be aligned with the flow of the glacier. We still don't understand everything about this process. We've been talking a lot with glaciologists about it, but it's something which we must take into account to reconstruct our events. And finally, this is the most fun, we found out that we have a bubble column in each of the holes. This is from the ice that was melted during the drilling and then refrozen, and the air that was released during that process got frozen into a bubble column in the center of the hole. We have one photograph of it, but we assume that this affects all of our holes. It is especially important for our low energy neutrino events, and so this is the scattering column. This is very clear ice, so most of the ice is very clear, but all of the impurities in the air got trapped in this column in the center. So what do neutrinos look like in IceCube? And I'm talking now about the very high energy neutrinos. So these are hundreds of TeV to PeV energies is what I'll be discussing for the rest of this talk. So you can have all three flavors of neutrinos in IceCube. And if you have a charge current interaction, then you get a W boson, and then outside of that you get the associated charge lepton. And so if it is a muon neutrino, then after the interaction, the muon will form a track through the ice, and in these pictures, the colors represent time, so red is early and green or blue is late, so this is going from up to down like that. And the size of each sphere represents the amount of light that was recorded by that photomultiplier tube, so the amount of charge, the number of photoelectrons. And so larger amounts of charge indicate higher energy. So the muon neutrino tracks, these muons, very relativistic, and so they can start outside the detector and go all the way through, or they can start in the detector and exit it. But if you have an electron neutrino, in that case, the electron immediately interacts with the surrounding ice and forms an electromagnetic cascade or shower. I'll use the word cascade for the rest of the talk. And these cascades develop over about 10 meters or so, and this looks almost point-like in IceCube because the horizontal distance between strings is 125 meters. So it looks almost like this spherical distribution of light, with light going out in all directions. And This shower or cascade signature is also seen for any neutral current event, regardless of flavor. That's a hadronic cascade. And then for tau neutrinos, that is one of my interests. And with a tau, because it has such a short decay length, you can actually see it decay in the detector. And so what you see is the initial interaction from the neutrino. That's a deep inelastic scattering reaction in all three of these cases at these energies. And then when you get the tau lepton out, it'll decay most of the time to hadrons, sometimes to electrons, sometimes to a muon. And that second cascade can be resolved from the first one if the energy is sufficiently high. It would have to be above hundreds of TeV in energy. So this is called a double bang signature or a double cascade. And so this is something that we're looking for to try and identify tau neutrinos. This is a simulation of a track in IceCube which shows the simulated photons. So that's what these lines are. They're the light moving out from the track. And so you can see at the beginning here, this is a cone. This is the Cherenkov cone because this is traveling at the speed of light in vacuum, and so it creates Cherenkov light in the detector. These are very high energy muons, so they do not emit their light evenly always. They lose a lot of light stochastically, Bremsstrahlung, other effects as they move through the detector. But you notice that the lines are kind of wiggly as they move out from the track. This is the effect of scattering in the ice on the photons. And with the track, we've still got a pretty long lever arm for reconstructing its direction. So our direction with resolution for tracks is about half a degree. The energy, obviously, it's not necessarily contained. It might be only partially contained or not contained at all. So the energy, we only get to about a factor of 2. For cascades, those are entirely contained within the detector, or can be. But the direction, as you can see, is quite poor because scattering quickly loses you any information that you had about the direction. Now, we do have some information. Direction resolution is about 15 degrees, but that is much worse than tracks. This is 30 times the size of the full moon. The energy resolution, however, is much better, is 10% for these high energy cascades because the light is all contained within the detector. So our backgrounds mostly come from cosmic ray air showers. So cosmic ray air showers produce muons and neutrinos. And the muons, they come to us from above. They're a downgoing signal. And that is the vast majority of our signal at trigger level. It's about 3 kilohertz of muons at trigger level. Neutrinos can come to us from above. We don't see them so much because of the muons, but they also come to us from below because they are low enough in energy to get all the way through the Earth. And therefore, we have this background of atmospheric neutrinos, and we see a few hundred of those per day. And so they are definitely neutrinos. Anything upgoing is a neutrino, but they are atmospheric rather than astrophysical. And this just shows the spectrum of the atmospheric neutrinos. In blue is muon neutrinos, in red is electron neutrinos. The pink here is the prompt spectrum, which is neutrinos from cosmic rays that induce charmed mesons, and therefore they decay right away before they have time to interact, and they produce neutrinos promptly. That's what the prompt means. And that's a steeper spectrum, but it's much, much lower in flux. And so we have not yet identified the prompt neutrinos. That is something we're trying to do. It turns out that the astrophysical neutrinos kind of mask out that signal, but that's still something that's on our to-do list, is to try and identify this prompt signal. So in order to reject this background, so we have most of our background coming from above, so one obvious thing to do is to look for upgoing signals. And we don't want to restrict ourselves to that, however, because the southern hemisphere sky contains the galactic center, which is an extremely interesting region, and so we want to be able to look at the entire sky. So in order to look at downgoing events, we look for contained events, events which are not coming from outside the detector, and I'll show you how that works. And we also, of course, look for events that are very high in energy in order to get away from this steeply falling conventional atmospheric neutrino spectrum. If you go away out here in higher in energy, past 100 TeV, then the atmospheric neutrino spectrum falls very rapidly, and what you see there is expected to be astrophysical in origin. So this shows our effective area for various types of upgoing events, and this is also another reason why we want to look at downgoing events as well. This is the effective area as a function of energy, and for horizontal events, you don't really see much effect due to energy, just rising effective area. But for the upgoing events, events which are coming straight up through the Earth, we do see a fall off as we get to higher energies because neutrinos at that energy actually do start to get absorbed by the Earth. So these are not old-fashioned neutrinos going through, a light year of lead without interacting. These are, 100 TeV neutrinos. The cross sections get larger, and so they do start to get absorbed. So if we want to see PeV neutrinos, then we need to look at downgoing events and have some sensitivity there. So we have two searches which I'll show here, both of which can be described fairly simply. The high energy starting event search, which we call HESI for short, if you see that acronym on the slides. This is a very simple search just for starting high energy neutrinos. So what we do is we take the detector and we turn part of it into a veto region. And so this is the detector as seen from above. The outer layer of strings all around is a veto. And we also have the top as a veto for 90 meters, so that's several layers of DOMs in order to get away from this cosmic ray muon background, which is so intense from above. We also have a veto in the dust layer. This is because the ice is just not characterized very well there, and a muon can sneak through more easily there, so we eliminate the dust layer. And we also cut off the bottom here, just the bottommost DOM. We require no more than 3 of the first 250 photoelectrons in the event to be in the veto region. Any more than that, we consider it to be vetoed. We eliminate that event. And we require at least 6,000 photoelectrons total in the event, which corresponds to a threshold of about 30 TeV. So the way the search works is, it's quite simple with the veto region. If we have a cosmic ray muon coming from above, it's going to be creating light all along its track. And we'll see some of that light in the outermost region of the detector, and so we'll veto that. Whereas if it's a neutrino, then it can come invisibly into the detector and then interact inside the detector, inside the veto region, and so that we accept as an event here. And of course, there is some background of muons and atmospheric neutrinos that can sneak past this, either in energy or in the veto, but this will get us to the point where we can detect astrophysical neutrinos with high significance. So this is one of the early events that we got from the first 2 years of our search. Back then we named them all after Muppet characters, so this is Bert. And so this is a real event, not a simulated event, so you don't see the light, but you see that the event is starting deep inside the detector, and then the light is spreading outwards in all directions. So this is a classic cascade. And the red is early again, the orange and the green as it goes outward or late, and you just see the light spreading out. And this is spreading out, the light is over hundreds of meters. Remember, it's 125 meters in between each row of strings. And the energy deposited by this event is about 1 PeV deposited in the detector. So this was one of the highest energy neutrinos ever seen at the time. Since then, we've gone a bit higher. And this is our highest energy contained cascade. This is Big Bird. And this was discovered in the 3rd year of the search. And so again, it looks like a cascade, the red starting in the middle and then the light spreading out. And that had an energy of about 2 PeV. So currently we've got 6 years of data, which are ready to show. We have a 7th year of data, which is currently in processing. And if this talk was 2 weeks later, I'd be able to show you that. But we'll be showing that at Neutrino 2018, which will be in a couple weeks, if all goes well. And so what this shows is the black represents the data binned in energy. So these are the events that pass the search. We have 80 events in 6 years. And the shaded regions are various types of backgrounds. Red is the atmospheric muon background, and blue is the atmospheric neutrino background. Pink is the fit to the charm or prompt component. And so this is an upper limit. It's an upper limit on the charm component. And then the best fit flux is shown in these dashed lines here. So it is consistent with the power law, although with a somewhat softer spectrum than we expected. Currently we fit 2.92 as the spectral index of these contained events. This here on the right is the plot of the flux, or the number of events as a function of the sign of the declination angle. Events on the left are downgoing, events on the right are upgoing. So you see we've got a nice lot of downgoing events. And the background is expected to be very suppressed for downgoing events because these events would be vetoed by accompanying muons if they were from cosmic ray air showers. And so this is a good indication that what we're seeing is not produced by cosmic ray air showers. The expected background in this time is 15 with fairly large error bars, atmospheric neutrinos, and 25 atmospheric muons. And putting this and the declination information together, this is an over 5 sigma rejection of an atmospheric only hypothesis for the source of these neutrinos. And so we also have a selection of through-going events. These are high-energy neutrino events, all upgoing. We don't allow downgoing because that would allow in the cosmic ray muon background. So for now, these are all upgoing. And the highest energy neutrino we've seen so far at all, so not contained, but just in general, was this one, which made APOD in September of 2015. And of course, all of the energy that's deposited in the detector is only part of the energy because this track started outside the detector and then exited. So not all the energy is deposited, but we modeled the amount here, and we expect the median expectation for the neutrino energy is 8.7 PeV for this neutrino. It is upgoing, but only slightly. So the atmospheric neutrino spectrum, what we get from the starting events, the contained events, is in blue here, so that's a 2.92 spectrum. We get a harder spectrum from the upgoing, through-going muon neutrinos, that's about 2.1. And so far, these are still statistically compatible with each other, but we are still investigating what exactly is the difference between these populations, what might be the cause of the different spectral indices that we fit. One thing to note is that the energy ranges are different. There's more low energy events in the starting events. So this is still in progress, is understanding the spectrum. Other questions we have which are outstanding, we cannot yet answer. Is there a spectral cutoff? Is there a high energy cutoff? Are there multiple power laws involved? Are there any angular or direction in the sky which have different properties? And so that's still something we're trying to answer. Just a quick mention of tau neutrinos. So this is one of the missing pieces of our picture. We do expect to see tau neutrinos from these sources because muon neutrinos we expect to be produced at the source from the pion decay, and they should oscillate into various flavors, and we should see equal numbers of all 3 flavors by the time they get to Earth. And so the double bang signature, you have the initial charge current interaction, and then you have the decay of the tau. One search that we did in order to try and get away from this well-separated double cascade, which would be, we'd have to be very lucky to see that, is to look at individual IceCube sensors and make use of our waveforms, these very detailed signals that we get from the DOMs, and actually look for what we call a double pulse. So actually you can see 2 bumps from the 2 cascades in this picture, even if they just look like one cascade in the event view. So we did not see any results from a 3-year search. There's an updated search that is coming. And one thing to note is that we did see a background in this search, which were not contained, but these are atmospheric muons which have stochastic losses very close to the DOM, and they can actually create a double pulse. So we need to have a containment cut in order to get away from those. We're also doing another search which is more similar to our traditional Cascade search, which is a likelihood search. So we do have a likelihood for the event shape, and we can do a double cascade likelihood. So in order to do this properly, you need to implement the most sophisticated modeling of the ice, including anisotropy and tilt, because if you don't take anisotropy into effect, it can actually mimic a double cascade or double bang. So this plot shows, this is sensitivity only, not results, but it shows the increase in sensitivity we would get by applying a tau identifier from this double cascade search. And what this plot is, this is a triangle plot showing the fraction of tau neutrinos we detect versus the fraction of muon neutrinos we detect versus the fraction of electron neutrinos we detect. And what we expect is 1 to 1 to 1, 1/3 of each, and that's right in the center of the triangle. And so if we only know tracks and cascades, okay, in that case there's a degeneracy between tau neutrinos and electron, then we get this larger dash contours here. But if we can identify taus with a double bang, then we get a tighter contour here. So again, that's something where the results of that search are forthcoming. Another thing which we're working on, and we're still, we have this new event selection, but we're still investigating the results of that, is partially contained cascades. And we did that in order to try and get more of the high energy events, to give us more volume. But if you work with partially contained events, you are of course running right up against your muon background, so these events have to be really scrutinized to see if they are in fact neutrinos as opposed to muons. And the reason why we're interested in getting to high energies, aside from just the fact that high energies are cool, is we want to try and go after the Glasgow resonance. And so this is resonant scattering of electron antineutrinos off of electrons in the ice that produces an on-shell W boson. at 6.3 PeV. And this is interesting because it would tell us something about whether there are antineutrinos, or the amount of antineutrinos in the astrophysical neutrino flux. For all other searches that we do, we cannot distinguish between neutrinos and antineutrinos. This is the only search we have that is sensitive only to antineutrinos. And so stay tuned for more information on this, but this is our highest energy candidate event, and it's at the corner of the detector, and so we're in the process of studying that. And we plan to have more results at TEVPA in this year, and then later on at the Ultra High Energy Cosmic Ray Conference. So now I'm going to talk about how we try and associate our neutrinos with astrophysical sources and work with other types of detectors in order to see, what is the source of these neutrinos. So the first thing we can do is just make a sky map. So we take all of the events from our starting event search and put them on the sky. This is an equatorial coordinate, so everything on the bottom half is in the southern hemisphere sky. For us, it's downgoing. Everything in the top half is northern hemisphere sky. For us, it's upgoing. And we just look and see, do we see a significant cluster? And the tracks are X's, and the showers are crosses, and the showers and the purple regions are the uncertainty. So of course the showers have much larger uncertainty than the tracks. And we do not see any statistically significant clustering here. This gray line here, that is the galactic plane in equatorial coordinates. And I think the galactic center is somewhere around here. So we don't yet see any statistically significant clustering from this search, but this is only 80 events. So we can open up a larger selection of events, which is all of our through-going tracks, including some at lower energies than the ones I mentioned. And we can even, we can open up the southern hemisphere sky to this by imposing a large energy cut and basically selecting cosmic ray muons that are very high in energy and seeing if any of them cluster, which would indicate they were neutrinos rather than cosmic rays. So we do not see any statistically significant clustering in this map either, and this is 7 years of data. And in addition to just looking for clusters with the neutrinos, we also scan through a list of catalog selected sources, gamma ray sources, radio sources, AGNs, various types of quasars, FSRQ, and blazars, also the galactic center, supernova remnants, starburst galaxies, anything we think might be a possible source of neutrinos, and so far we do not see any statistically significant correlation of neutrinos with those sources. We can therefore put constraints on various source classes, specifically how much do they contribute to the neutrino flux that we observe. Our strictest constraints are on gamma ray bursts. We have never seen a neutrino in temporal and spatial coincidence with a gamma ray burst. And so this, because there's a tight time window around gamma ray bursts, that allows us to eliminate a lot of background and set the tightest constraints. So gamma ray bursts contribute less than 1% of the high energy neutrino flux. We can do other searches, for example, recent ones, so these all came out in AppJ last year. We did a stacking search with the Fermi Blazer catalog and just stacked all those on top of each other and looked at the neutrinos. We did both an equally weighted check, so all neutrinos weighted equally, and also neutrinos weighted by the gamma ray flux of the gamma ray sources. And we found that they contribute less than 27% or less than 7%, depending on how you weight them. We did a search of the galactic plane. That contributes less than 14% of the neutrino flux. So all of these things mean that we do not see a statistically significant correlation of the neutrinos with these objects, and therefore we can set an upper limit on how much they contribute to the neutrino flux. So we do not yet have a smoking gun source. And we keep looking at various Fermi sources, not only steady state, but of course we also want to look at transient sources as well, in addition to gamma ray bursts. So gravitational waves have been a very interesting new addition to the multi-messenger universe, and in just a couple of years they got their first multi-messenger source, which was the neutron-star merger. And so we did a search for neutrinos, not only IceCube, but also our sister experiment in the Mediterranean, Antares, similar concept, but in water instead of ice. And also the Pierre Auger Observatory just happened to have be properly aligned to be sensitive to neutrinos from this source. So this is the neutron-star merger and the associated gamma ray burst right here. And what we do when we search for neutrinos from a gravitational wave source is we look plus or minus 500 seconds, within plus or minus 500 seconds of the gravitational wave trigger. And this is just motivated on observations of gamma ray bursts, of precursors, and kind of the most conservative window we can set where we might expect to see neutrinos in association with these objects. And so it's 1,000 seconds, and that's a long time in IceCube. We do see hundreds of atmospheric neutrinos per day. So that's what we see here, these crosses, the X's right here. But none of them were associated in space with this object. They were just scattered around the sky. And Antares also had some events, but did not see any that were at the same point. Unfortunately, this event was in the downgoing region. So it was the southern hemisphere sky for IceCube, and it was in the downgoing region of Antares, which is marked by everything above this dash line here, which means our background is worse there. So it would be nice to get a northern hemisphere source. Also one with the axis and jet maybe pointed more towards the Earth. Auger is also sensitive to neutrinos, only in a very narrow band, which just happened to coincide with the source at the time, but did not see any events. So, but we are certainly going to be continuing to monitor these events as they come out from LIGO's next observing run, and we'll keep searching for neutrinos from those. So we want to try and get electromagnetic partners especially involved early on. So for the past year or so, past 2 years now, we have been sending real-time alerts from the South Pole. So we send these alerts with a latency of less than a minute. Median latency is 33 seconds. And so we have a filtering system which picks out interesting events, and then they're checked on the monitoring system in the south, then they're sent to the north. And then we've got a couple of different alert streams. This is IceCube jargon, but EHE is our through-going track alert. HESI is our starting track alert. We only send tracks, we don't send cascades at the moment, because telling our electromagnetic partners to point at a 15-degree area of the sky is not very helpful. And then we send out public alerts through the, there's an AMON system. This is a multi-messenger network, and also through GCN. And so we've sent 13 alerts since 2016. And we usually send the first alert, as I mentioned, within a minute. And then after a few hours, we send detailed follow-ups based on reconstruction of the event and try to send a better estimate of the angular error of this event and any changes in its location that may have happened in reconstruction. And so this is a picture of one of our through-going track events. Very pretty. This is more than a PeV of deposited energy in the detector. And so the energy for the starting tracks, they start at 60 TeV for alert events. For through-going tracks, we have a higher threshold, that's 500 TeV. And each of them sends about 4 alerts per year. And these are non-overlapping samples. Through-going tracks do not pass the starting track search, so these are non-overlapping. And the expected signal events per year, that is the expected number of astrophysical events over atmospheric background, is about 1 for the starting tracks and 2.5 to 4 for the through-going tracks. So we are working on improving our alerts based on feedback from the community and also things we want to do. So some upcoming improvements. We have a new starting event selection which is in progress. It has not yet been approved for release, but this will be more downgoing events of lower energy. So it's got stricter veto conditions, but this will add something to our picture. Eventually we do want to send out cascades, at least for the use of wide field observatories, but we're still working on that. And we do want to improve our astrophysical event purity, reduce the number of background events, so we're working on that. So we're updating our selections, and also we'll be updating the information we put in the alerts to make them more transparent. So yeah, this is a very interesting thing, and I really wish this talk was in a few weeks, because I can't really say much more than's on this slide. But in September of 2017, right in the teeth of the IceCube collaboration meeting in Berlin, we sent out a through-going track alert, and it was spatially coincident with a known blazar. So this is a Fermi Blazer, was already in the Fermi catalog, and it was flaring at the time. It had been flaring for a few months. And what really got everyone going was that then MAGIC followed up. This is a high-energy ground-based gamma-ray telescope, and it achieved the first detection of this blazar in high-energy gamma rays, so 5-segment detection above 100 GeV. In the weeks following the IceCube detection, they had bad weather when they did their initial observations, so the detection came from a later observation. Sent out an ATEL here. And so there's over 20 ATELs associated with this event, and we've been working with our partners to put together a paper, which is embargoed, so I can't say anything more. So, Now talking about the future for IceCube. So we still have not, exploited everything that IceCube can do. We're still working on understanding the ice better and improving our reconstructions. But of course, we want to build a bigger detector. So the name of our putative upgrade is IceCube Gen 2 because we want to be terribly clever and name it after a penguin. And the Gen 2 observatory would consist of a high energy array. So this is IceCube here in red. So we would surround it on one side at least with more strings. We can't surround it equally on all sides because there's restrictions on where we can drill at pole. And then we would fill in our center with more strings to make a precision array called Pingu. This is for doing atmospheric neutrino physics, especially going after the neutrino mass ordering, which would be a very nice complementary measurement to everything that's going on in the accelerator neutrino world. And we would also have an extended surface array, so that's what's shown here on the surface. The ice-top array is exactly coincident with IceCube, so it doesn't veto much more than things that are directly downgoing, but this would veto more and allow us to get a better grip on the southern hemisphere sky. And so the questions we want to answer are, even if, the best case scenario for IceCube, we won't have as good of an idea of the point sources of neutrinos as we would with this expanded detector, especially with more track detections. We want to know more about the spectrum of the neutrinos, or, how hard is it, how soft is it, are there multiple spectral indices involved, is there an energy cutoff? We want to know more about the flavor content, about Glashow events, and then, as I mentioned, we want to do neutrino physics at low energies and do the neutrino mass ordering. So this is a plot showing what we would be able to achieve with Gen 2. So this is a nice multi-messenger plot. This is the Fermi lat diffuse gamma ray flux. This in green and blue is the TA and Auger cosmic ray flux, and then in between is the IceCube 100 TeV PeV neutrino flux. And this gray area is where we are now, okay, in terms of our uncertainties and our measurements, and the orange represents where we would be with Gen 2, so we would get a much better measurement of the spectrum with the higher statistics. So the first phase, it was formerly called Gen 2 Phase 1, but is now called the IceCube Upgrade, and this is our proposal, which is currently under review with the NSF. And this is to restart the drilling process, get the drill out of mothballs and update it, and start drilling some new strings. So the proposal calls for 7 new strings in the center of IceCube in the deep core area. Not as many strings as Pingu, but that's kind of moving in that direction. The physics we would do would be neutrino disappearance and tau appearance in the atmospheric sector, so down in the tens of GeV energies, and also more precise calibration of the ice and the optical modules. So the strings we're looking at would be strings with 2.4 meter spacing in between the modules, so over 100 modules on the string, so make it a very dense array. And then the space in between strings would be on the 10 to 20 meter level, which would enable us to probe the ice at lengths that are shorter than the IceCube scattering length for the first time. So one thing we really want to do with this upgrade is try and improve our reconstruction. So these are Cascade events, the high energy starting Cascade events in IceCube, and this is the per event angular error for each one, and this is measured by basically doing a lot of simulations and seeing how often we would measure that particular angle. And as we go to high energies, so this is the angular error versus energy, for statistical only, we expect to be able to get down to below 5 degrees, which is still a big improvement over 15, but when we actually look at our events, we don't see we're getting anywhere near that, so we need to understand the detector better in order to do that. There's a lot of aspects to that, understanding the ice, understanding the cable shadow, understanding how to handle bright DOMs in the center of the events. That's still something that's a work in progress. And so we're looking at putting new calibration devices in the upgrade in order to improve our modeling of the ice and of the DOMs. This is one of the new devices under study, which is the Precision Optical Calibration Module, which has already been tested in water in Lake Baikal, as well as updated LED flashers and other devices. For the sensors for Gen 2, we're looking beyond the IceCube model in 2 ways especially. One of them is to try to go for slimmer designs. This is to save drilling costs. So the wider the hole is to get the module down, the more fuel you use, and that's one of the major expenses involved in IceCube. The other is just increasing our photocathode area and being sensitive to more directions. All IceCube PMTs are downward facing. We want to have something that's upward facing as well. So some of the ideas that are under study, the MDOM, this is inspired by our friends at KM3net. They have a similar design in KM3net. And so this is a lot of 3-inch PMTs set in this kind of fly's eye design with sensitivity in all directions. Our colleagues in Japan are developing the D-egg, which is a dual PMT module, just one PMT up, one PMT down, in a slim egg-shaped case. Okay, so again, to make the drilling cheaper. And we're also looking at other technologies. We've always used only PMTs, but there are wavelength shifting optical modules, fibers, a lot of other things that are under study. For the surface detector, we've got two things that are under study. One is just scintillator, which is a good workhorse for cosmic ray detection. That was high threshold and high duty cycle. And then we're also looking at gamma ray detectors on the surface. This has a very low duty cycle compared to scintillator. It's about 10% because we have to deal with the moon and auroras and all kinds of things. But it also has a much lower threshold, so that would be an interesting component of our VTOL. We're also looking at just updating the IceCube Dom. Since this is a known design, it's very reliable. It's been in the ice for many years now, which would look fairly the same, but we would update the electronics, more off-the-shelf digitizers as opposed to the custom-made digitizers that we use now, and updated LED flashers, and updating how we do the calibration of the module on board. So in summary, so we have astrophysical neutrinos. We're still trying to figure out their properties and where they come from, and it's a really exciting time to be working with our partners in electromagnetic and gravitational waves and cosmic rays. And there are a lot of observatories that are in progress, being upgraded and in planning in neutrinos, gravitational waves, cosmic rays, and all kinds of arrays on the ground. This only scratches the surface. Thank you very much for your attention.
All right, thanks, John, for that really nice presentation. Questions?
Well, actually, I have one. The first bullet there is, of course, the big number one important one. But now we've got a family of these, and now, how many do you have to get before it's old news?
At this point, because the individual events are becoming more interesting in some ways than the ensemble, right? Because we send them out as alerts, and if they have something that's associated with them as a multi-messenger partner. So I would say it's not yet at the point where we're thinking about old news, because we need more of them in order to really pin down the spectral characteristics. So we're past 5 sigma, so that's kind of one threshold for old news. But also, in addition, trying to identify tau neutrinos, that's still out there, and identifying Glasgow resonance events, that's still out there. And so it's not just a matter of the ensemble numbers, but the individual properties of the events.
Okay, but the big mystery is sort of established now. There is a very significant flux of astrophysical neutrinos, and as you say, the PeV scale, joule, basically. It's very high energy cosmic ray energies. And you sort of know now how many there are. And I'm a little confused about what, if anything, one has learned about the cosmos.
So far, we have not yet been able to complete that picture. So right now we know that there are astrophysical neutrinos, but until we know where they come from and are able to get a better handle on their spectral characteristics, so that's still to come.
Can you comment on maybe what the significance is of the fact that you haven't been able to associate them yet with with various sources?
Well, it seems to indicate that instead of the sky being dominated by a few large close by sources, it's maybe dominated by more fainter, further sources. And so we're still trying to understand that. I mean, particularly it was a bit of a surprise to us not to see anything from gamma ray bursts. So we set limits that were much more stringent than the models at the time. And of course, then the models evolved. But that was an interesting thing. We were sort of expecting that we would see something from gamma ray bursts. Was predicted by the original round of models that was available at the time IceCube was constructed. But overall, that's the message we're getting just from the fact that we don't see statistically significant clusters early on, is that we don't have a close bright source.
More questions?
What's the
timescale for the upgrade that you're talking about?
So if we got funding tomorrow, the timescale is 5 years for the first part of the upgrade. That's the phase 1 part of the upgrade, the 7 strings. The timescale for Gen 2, that would be more of a 10 to 15 year timescale.
And the surface array?
In principle, we can roll that out a lot faster because we don't have to wait for the drill. That's the main thing that holds things up for the in-ice array is the drill and the fact that we can only drill at certain times of the year. With the surface array, there the challenge is just how do we actually manage these very remote stations that are very far from the current footprint of IceCube. So currently, everything is connected by cables to the IceCube lab, and the winter rovers can walk out to it, and it's all fairly accessible. But if we're talking about much larger surface veto, then we would need remote stations, things that are not necessarily attached by cables, and that's a design challenge. We are currently putting out scintillators at the pole in order to basically account for the fact that our ice top tanks are becoming buried in snow, so we're losing the electromagnetic component of the showers. Still get the muons, of course. So that's the scintillator upgrade is already ongoing as a surface upgrade, but that only coincides to the existing ice top tanks. That's not any larger in area.
And there's no radio in the upgrade?
So that's a question. So whether radio would be officially included in the upgrade or not, we don't have a full proposal for the upgrade, only for the phase 1. The phase 1 does not include any radio. So right now, the radio experiments at the pole, they're going after the cosmogenic neutrinos. They are a separate experiment, but they're kind of within the IceCube umbrella. They share some of our facilities in terms of the infrastructure. It would be ideal to have radio as part of the upgrade. But overall, the radio is always going to be much more certain to see things that are outside of the optical detector, because they're always going to have a much larger field of view than the optical detector, where events must be at least partially contained.
Could you describe drilling a hole? How do you get your stuff in there after you've drilled the hole? Doesn't it freeze back up?
It takes a little while to freeze back up. So we can get the string deployed within 12 to 24 hours. And so basically there's a giant hose reel, and we lower the cable, and as the cable goes by, we attach the DOMs to the breakouts, which are already on the cable, and then we lower the entire thing. And so we've never had a string in IceCube get stuck. It did happen to Amanda, our predecessor. We had one stuck string there, but we know a lot more than we do now. So the top priority once we get the hole drilled is to get the material deployed as fast as possible. And of course, the string freezes from the top down, right? The hole freezes from the top down, so that makes it very important to get it deployed as fast as possible.
What's the temperature halfway down?
Oh gosh, it's between -50, I think, in the uppermost modules, and gets towards, I think, -20 in the bottommost modules, where it starts to get closer to the Earth, and it's warmer, closer to the bedrock. So in between, somewhere in between there, but it's between about -30 and -20.
We have a couple in the back, maybe. Either.
Is there anything you would do differently in the drilling process to reduce the bubbles?
So that's something we're thinking of for Gen 2. We're looking into degassing and having more control over the process, but we've never tried anything like degassing on that scale, and it wasn't really something that was in our minds, that this would happen. So we do plan to try degassing for the upgrade, but whether it'll work or not is still to be determined. The other thing which we are definitely going to do differently, this is more of a technical detail, but to keep contaminants from the drill water out, because we basically use some of the drill water as return water, and so some contaminants got into the water. In some of the holes it's not really noticeable, but there's a couple of holes where the absorption of the ice in the hole is noticeably lower than the others, and it doesn't make any difference for the large scale physics because these events are so bright, but it is something we want to avoid going forward in the future.
If you believe the consensus, the neutrinos have a mass, according to textbooks I read, they'll travel less than the speed of light. And I'm wondering if there's anything in your data that could reflect or show insight or anything related to that. For example, if you have a simultaneous source of a gamma ray burst far enough away, which is also putting out neutrinos, and those are moving slower, you wouldn't expect them to arrive at the same time. So anything in your experimental method that would reflect on neutrino mass?
So I don't think we would be sensitive, because these are extremely relativistic, so I don't think we'd be sensitive necessarily to the mass. I have talked with people in LIGO about, if we got a neutrino and a gravitational wave event at the same time, or if we got a neutrino and, gamma ray event, we would at least be able to set some limits. But of course we have to take into account the modeling, right? The gamma rays and the gravitational waves and the neutrinos aren't necessarily all produced at the same time, so there is some uncertainty there. And so I think the best handle we've got yet on neutrinos traveling at the speed of light is, as far as from that point of view, is supernovae.
Well, could you place even a limit then based on what you're saying that the neutrino mass, and how big would the mass have to be that you would see an effect?
Yeah, I don't know off the top of my head what kind of limits we could place. At present, we can't place any because we don't have a definite association of a neutrino with another type of messenger.
More on the hole drilling. How accurately do you know the position of the holes and the spacing of the sensors, and is there any way of post-processing the data so that you can figure out more accurately what the spacing actually is versus what you intended it? Yeah,
this is right in my wheelhouse. this was my job as a postdoc. So the spacing between sensors, that's easy. We measure that with a laser ranger, and so we don't. And then we measure it again in the ice with the flashers, LED flashers, and so that's all good. The spacing between the strings, that's more difficult. So we surveyed the positions of the strings, and then we used drill data to see how straight the hole was going down, and it's straight to within a meter. And then to measure the absolute depth of the strings, that was actually more complicated because we used pressure sensors to measure the depth, and every once in a while one would fail. And so we used the LED flashers in order to make those measurements of that. The kind of the overall depth of the detector we can also measure with muons from IceTop and just measure the time difference, so that gives us some handle there. And with the strings that are closest together in deep core, we have done trilateration measurements, basically to try and see, do we agree with the drill data? And we do, but we can't do much better than the drill data. So we'll need modules closer together or a different technology in order to get a better accuracy. So currently our accuracy is about a meter, which is more than enough for us. But in the future, for Gen 2, especially when the strings are much further apart in the upgrade, trying to measure that with LED flashers is going to be extremely difficult because of the long distances. There's just so much scattering. So we're planning to put acoustic sensors on the DOMs in order to measure their distance from each other. But that's not a technology we've yet tried in IceCube.
Okay, I have one more. The tau neutrino identification is super interesting. Can you talk a little bit about what sort of, how that'll play into oscillation measurements? If you can use that information, is it more principle, and sort of what other physics you can get out of that?
So in the case of the tau neutrino, that is something we need in order to get away from the degeneracy that we have between cascade events. And so what we're interested in there's a couple of things that we're interested in. First of all is just we do expect to see tau neutrinos from astrophysical events, and we don't expect to see tau neutrinos at that energy from the atmosphere. There's just not enough charm. So seeing them would be a smoking gun that this in fact was an astrophysical neutrino just as a single event. So that's interesting. In terms of the physics of the source, so there are various models, okay, which can predict different fluxes of neutrinos at the source. The standard pion model, that's just 2 muon neutrinos, 1 electron neutrino, no taus. By the time it gets to Earth, it's 1 to 1 to 1. But if, for example, you have a source that's all muon neutrinos or all electron neutrinos, and there's various models of different places along the spectrum, you can get different ratios where it's not quite equal. Now, with a few tau neutrino detections, which is at most what we would expect, statistically would expect maybe about 2 at most from the methods I'm describing in the data set that we're looking at now, 2 to 3 maybe. And that in itself is not enough to distinguish between those models because the contours are still encompassing all of those possibilities. Just theta 2-3 is so large that no matter what you start with, you end up with a lot of tau neutrinos at the end. But that's what it would enable us to eventually go after is the physics of the source. Is there any weird neutrino physics going on, any new models, or is there anything strange going on in terms of the astrophysics that's not giving you the typical pion model? With the Glasgow events, locating antineutrinos would tell us that there was negative pions in the original environment, and that's something we expect more from proton-proton than proton-gamma, so that would give us some insight into the astrophysical environment. Nothing we can do with IceCube I would expect to be able to give us a statistically significant measurement, but it would be indications, and then we'd be able to do better with Gen 2. So that's why those are important for understanding the astrophysical environment as well as the physics.
Yeah, I guess that tau neutrino wasn't directly observed until like the late 90s anyway, so it's really cool to think that you could actually also do it with IceCube. Are there any more questions? All right, if not, let's think on it. I know, I'm sorry. I know. The time that